Hey guys, and welcome back to another video on the channel. In today's video we're going to be finding the Fourier series of a periodic function given on one period by pretty much f of x is the absolute value of x on the interval negative pi to pi pretty much, okay? So this function here pretty much means whatever x value you plug into it, positive or negative, it's just going to take the absolute value. So negative values become positive and positive values remain the same. So a good way to think about this function is pretty much imagine the line just y equals x. So this line that looks like this. And pretty much all these negative outputs here just get reflected up here. So it pretty much looks something like this. So you can rub out this line now. And then you have something like this here. And this is what y equals absolute value of x looks like. So y equals the absolute value of x, okay? And it pretty much just keeps going forever. But on this particular thing, it's just between negative pi and pi. So just goes up to here. So this is pi and this is negative pi, okay? Now it wants to find the Fourier series of this periodic function. So pretty much imagine this function here, but it's pretty much getting copied and pasted every couple intervals. So for example, if I were to extend this line, it would then look like this here, and then that same interval, so this would be 2 pi now, and then that same interval there pretty much, okay? So it goes indefinitely that way and that way pretty much. So that's what it means for it to be periodic, okay? So to find the Fourier series of this thing, we need to work out what the period is. So the period is pretty much when does the cycle start repeating. So pretty much this distance here. So pretty much it starts repeating itself over and over across that distance. So from negative pi to pi, that distance there is pi, that distance there is pi. So that means the period, so your period is 2 pi. So double that, okay? So every 2 pi it repeats itself. So now we know what the period is. We could probably work out its Fourier series, okay? So a Fourier series is pretty much approximating a periodic function using sines or cosines. Now, the more sines and cosine terms you use, the more accurate it becomes. But if you use an infinite number, then it basically becomes exactly the same. So f of x, is the same as this one here, but f of x can also be represented as a naught, so your starting average value, plus an infinite series from starting from n equals 1 to infinity of a of n cos of nx plus b of n sine of nx, okay? So pretty much the reason why n equals 0 isn't included, well, it is actually included. It's already been put out there pretty much. If you put n equals 0 in here, you get cos of 0, which is 1, so you get a naught. And b of 0 doesn't exist because sine of 0 would be 0, okay? So your n equals 0 is already pretty much included with that a naught, okay? Now to calculate these particular coefficients here, we need to work out a couple of integrals, okay? So pretty much a naught is pretty much 1 over the period, pretty much. What would that be? Oh, not the period. 1 over the period from the integral of negative a half the period, so L on 2, and L on 2 here, of f of x, pretty much, okay? Now, since the period is 2 pi, so L is 2 pi, pretty much. So what we're going to pretty much have here is just pretty much a naught is 1 on 2 pi. The integral, so let's just move this out of the way, we'll make this a bit smaller. So we get the integral negative pi on, or just negative pi to pi of pretty much f of x, which is the absolute value of x, okay? Now the absolute value of x, when you think about it, it is basically it is an even function pretty much, okay? So since it's an even function, it pretty much can be reflected on both sides. So what that means is this side outputs are the same as this side's outputs. So since it's an even function, it's being integrated over symmetrical bounds. Pretty much this area here is exactly the same as this area here on this interval. So if we just work out one of these areas and times it by 2, you get that exact area pretty much, okay? So what that means is this integral here can be changed. So it would be a naught is still equal, so it would be 1 on 2 pi. But you can change the bounds now. So you can change that to a 0. And then you can change that to pi. But then you can put a times 2 at the front, okay? And that's just the value of x, because the absolute value is just the same as x. And you can see those 2's cancel out. So you get a naught equals 1 over pi. The integral from 0 to pi of x dx, okay? Now to work this out, you pretty much got to use a power rule, so add 1 to the power divided by the new power, so a naught is 1 on pi, x squared on 2, 0 to pi. So pretty much we get a naught, just subbing in pi first, so we have that 1 on pi at the front. So you get pi squared on 2 minus 0 squared on 2. And we can see straight away that is just nothing. So your a naught is 1 over pi times by pi squared on 2. So you can see we get pi on 2 as our a naught. Okay. Now, we can work out the rest of our coefficients using a couple other integrals. So all I'm going to do pretty much, just to save time pretty much, is just move this downwards. So we already know what a naught is, okay? Now to work out a of n and b of n, you've got to work out a couple integrals. So since the period is 2 pi, the following integrals will be used to calculate everything. So a of n will be the 1 over half the interval, so pretty much it will be pi. And it'll be integrated between those same intervals. So negative pi to pi of f of x cos of nx dx, and b of n will be 1 over pi. So this is just because the period is 2 pi. That's why we have these particular things here. If it wasn't, then they would change, okay? So it would be 1 over pi, same interval, negative pi to pi, f of x sine of nx dx, okay? Now, before we even do anything, we know f of x is the absolute value of our x. I nearly wrote pi there. We can work out what this is straight up, okay? F of x is an even function, okay? Sine of x is an odd function. Now, if you have an even function times an odd function, so this even function times an odd function, you get an odd function here, okay? Now, if you integrate an odd function over symmetrical bounds, so pretty much if you integrate from, let's go, negative a to a of an odd function, you get 0, okay? So this result here, no matter what f of x is, since f of x is even and sine is odd, this entire thing is an odd function. So the whole thing's just going to be 0, okay? So we can just say straight away, b of n is 0, okay? So that means in our Fourier series, this term doesn't exist. All the sine terms are gone pretty much, okay? So all we have to do is work out what a of n is pretty much, okay? Now there will be an a of n, otherwise there will be no Fourier series, okay? So all we do is pretty much, instead of writing the absolute value of x, we can just write it as x because we're taking to pretty much one side. And since it's an even function, we can do the same property that we did above with a naught of 0. So we can pretty much change it from negative pi, so from going from negative pi to 0 to pi, and then putting a 2 at the front because it's even. So that means we can just change it like this. So a of n is 1 on pi, bring a times 2 at the front, and change this to a 0 because it'll be the same area, pi to x cos of nx dx, okay? So at the front we have a of n is 2 on pi from 0 to pi x cos of nx dx. Now to work out this integral here, we need to do integration by parts because we pretty much have two functions times each other, okay? And there really isn't a product rule. Well, integration by parts is a product rule for integration, okay? So if you integrate pretty much two functions into each other, you need integration by parts. Now the following formula is pretty much here. So integration by parts basically means we have to label one of these as a derivative and one of these as a function we're going to differentiate, okay? So pretty much we want to choose one that integrates easily and one that differentiates easily, okay? So the one you want to pick to differentiate easily is a function that is going to disintegrate over time. So pretty much you're going to choose this one to be your u, okay? Because if you differentiate that, u dash will be 1. A cos or an Euler term will cycle, so you don't want to choose that to pretty much differentiate, pretty much. If you chose x to integrate, you would have pretty much x squared on 2, and you would have something worse than what you started with, okay? So in this particular example, u is going to be x, and v dash will be cos of nx, okay? So all we've got to do now is work out what u dash and v is. So differentiating x, you get 1. Integrating v, So the integral of cos will be sine, so sine of nx, but you have to divide by the differential. So the differential of nx would just be n, okay? So that's where we get that from. So writing this into the formula, so pretty much if I just chuck this to the side very quickly, we'll make that a bit smaller. So all I'm doing is looking at this integral. So the integral of x cos of nx is the same as pretty much u times by v. So x times by sine of nx over n minus the integral of u dash, which is 1, times by v, which is sine nx on n dx. Okay? So now we got to include our bounds. Because we had a 2 on pi at the front and from 0 to pi. Here we can just put in the square brackets, 0 to pi, and we can't forget that 2 pi at the front. So this is going around everything here. So 2 on pi, 2 on pi, yep. And then forget the bounds here, okay? So pretty much we've got another integral we need to work out. Now we probably should evaluate what this is going to be straight away, okay? So just looking at this square brackets here. So you have x sine of nx on n, and your bounds are 0 and pi. If I plug in pi, I'm going to get the following result. I'll get I'm going to get pi sine of n pi on n, and then if I plug in 0, it'll be minus 0 times by everything, so the whole thing is 0 here pretty much because you have that 0 on the top. Now, looking at this is basically saying n multiples of pi. So remember, n is an integer, a discrete number, so pretty much it can be 1, 2, 3, 4. Now sine of pi is 0. Sine of 2 pi is also 0. Sine of any multiple of pi is 0. So that thing is just gone. So this entire thing in this integration by parts is just gone. So we can just rub it out straight away. Okay. So all we're left with is pretty much this back integral here. So I'm just going to rub all this out so I have a bit of room. So all I'm going to do is just move this guy just a little bit closer. Yoink. Righto. So if I just rewrite this, we just grab 2 on pi, and we can chuck that negative out the front with it as well. And we have the integral from 0 to pi of sine of nx on n dx. So integrating this, so the integral of sine is going to be minus cos, so we'll have the minus 2 on pi at the front, but we'll have here is negative cos of nx, divide by n again, so you get an n squared on the bottom, and you have 0 on pi. You can take that negative out the front to cancel that negative, so what you'll have is 2 on pi, and then you'll have positive cos nx on n squared, 0 to pi. So now we're going to plug in everything. So first of all, we'll have the 2 on pi at the front, cos of n pi on n squared, minus cos, this will just be 0 on n squared, okay? Now, cos 0 is 1. Multiples of cos, it doesn't really change, it just fluctuates pretty much, okay? So for example, if you have cos of pi, you're going to get negative 1. If you have cos of 0, you get 1. If you have cos of 2 pi, you also get 1 again. So if you have cos n pi, it pretty much oscillates between 1 and negative 1 consistently, because n has to be discrete, so it has to be 1, 2, 3, 4, etc. So you can rewrite cos of n pi as just negative 1 to the power of n pretty much. So if you go n is 1, you get negative 1. If you get n is 2, you get positive 1, etc. Okay, so you can replace this bit here with just negative 1 to the power of n. Okay, so pretty much what we have is 2 on pi, negative 1 to the power of n on n squared, and this is just 1, so we have minus 1 on n squared, and we can combine those because we have a common denominator of n squared, so we can just go, that is 2 on pi, negative 1 to the power of n, minus 1 on n squared. And if we want, we can leave it exactly like that, or we can take out that factor of n squared, whatever. So pretty much a to the n is going to be 2 on pi n squared, brackets, this thing right here, okay? So now we've worked out what that is. We know a naught, what was a naught? I forgot it, it's up here somewhere. A naught is pi on 2. So a naught is pi on 2. So pretty much for our Fourier series, so f of x is a naught plus the infinite sum, so n equals 1 to infinity of an cos nx plus bn sine of nx. Okay, so we know what this is, we know what that is, and we know this thing is 0. Okay, so our Fourier series, so for f of x equals the absolute value of x between the intervals from negative pi to pi, this is our Fourier series. F of x is pi on 2 plus still the infinite sum from n equals 1 to infinity of 2 on n pi n squared, brackets, negative 1 to the power of n minus 1 times by cos of nx. And that, ladies and gentlemen, is our Fourier series for our function here, okay? If you have any questions about this one here, leave something in the comments and I'll try my best to answer it. But in the meantime, I'll see you in the next video. See ya!